Okay, so today our speaker is Aristov from HIT, which means Harbin Institute of Technology. And he will tell us about algebras of free C-infinity functions. Please.
Okay, thank you very much. So I'm glad to see you all, and to hear at least. So yes, my topic is algebras of free C-infinity functions. Sorry. У меня зависло. Меня слышно?
Слышно.
Да.
Почему-то не меняется слайд.
На компьютере зависло?
Все, отлично. Okay. So this talk is some certain continuation of my talk 2 years ago, so September 2021. So I begin with motivation. If we consider elements of a free algebra in pure algebraic sense as free polynomial functions, so it's natural to consider the elements of algebras introduced by Joseph Taylor many years ago as free holomorphic functions. There is two versions of such algebras. I do not need definition here, because I want to find a definition of an algebra of free C-infinity functions. And I suggest to use to define them the envelopes with respect to the class of Banach algebras of polynomial growth. But this class of Banach algebras has such properties that all reducible representations are one-dimensional, and also algebras are only over a field of real numbers, not complex numbers. But nevertheless, these algebras may have a big radical, and so this, in some extent, compensates the problems with reducible representations. So this proposition is a reformulation of a result of Polyjara and Foyers, that for an element of a Banach algebra of real numbers, these two conditions are equivalent. First is that the norm of the exponential of imaginary exponential of element b, here s is a real number. So this norm has polynomial growth. And the second condition is that there is multiplicative functional calculus from the algebra of functions with continuous nth derivative for some interval. And multiplicative functional calculus means that there is it is a continuous homomorphism compatible with the map from the identity function to our element b, which we fixed previously. It's interesting that the equivalence in the proof of that the property 1 implies property 2 used Fourier transform. And obviously that all elements of the algebra as Cn satisfy this condition. So here I mean that Sn is the functions in Cn are real valued also. And so we say that Banach algebra is of polynomial growth if the conditions of this proposition hold for every element. And this is in some sense new, because the property of individual element, of a single element, this property is well known. But when we want this property to hold for every element, this is essential restriction is sufficiently strong restriction. But it's important that the definition can be applied to non-commutative algebras. And the first non-commutative examples are the algebra of triangular matrices, real with real entries, of course, and the algebra of Cn with values in Tp, with values in triangular matrices. And these are the main properties of Banach algebras of polynomial growth. First is that if we take a quotient over a closed ideal, then the property being of polynomial growth preserved. So if B is a polynomial growth, then B over I is of polynomial growth also. Also, if B is of polynomial growth, then it is commutative modular radical. And the radical itself has the property that it is nilpotent as a subset of B. But by radical, I mean the Jacobson radical, the mutual kernel of all Gibson representations. And note that if B is not commutative, then it is not a self-adjoint subalgebra of a sister algebra. So the next step is to consider the class of projective limits of Banach algebras of polynomial growth, PGL. And this class has similar properties, at least first two. This class is stable under quotients over closed ideals, and every algebra in PGL is commutative modular radical. As to the third property, this property does not hold for PGL algebra in general, but this is not essential here. So the natural example is now is the algebra of C-infinity functions on some manifold with values and triangular matrices. If you want to get some other non-commutative examples, we can use analogues. So I give a general definition of an envelope for some class of a Banach algebra. Banach algebras over C or over R, it doesn't matter. So if you take a topological algebra A, then the envelope of A with respect to the class C, the pair of algebra and the homomorphism, where algebra A hat C, the projective limit of algebras in C, and the homomorphism is continuous homomorphism from A to this envelope. And we have the following useful property. For every continuous homomorphism from A to a Banach algebra in C can be extended to a continuous homomorphism from A hat C. It is easy to show that the envelope exists when C is stable under finite products and closed subalgebras. And for example, this holds for the class of Banach algebras of polynomial growths. So we can consider envelopes in this class. And so I denote the envelope in this class by A hat PG. So the basic this proposition is basic for us, so that the envelope of the algebra of polynomials, commutative algebra, is in fact the algebra of C-infinity functions on Rn. And the proof use the existence of functional calculus for several provident elements. So this is similar to the result of Polagera and Foish. but not for one element, but for several elements. And now we turn to free algebras. So consider the free algebra with M generators over real numbers. And the elements can be considered as free polynomial functions. And so I propose to consider to treat elements of the envelope as free C infinity functions. And in fact, C infinity on RK, RM, is a free commutative PGL algebra. But the envelope of the free algebra is a free PGL algebra in general. So our next goal is to give an explicit description of this envelope. And to do this, we represent the free algebra as the universal enveloping algebra of a free Lie algebra, FF. And also I assume that the number of generators is 2, because in general case, the statement of results and proofs are more complicated. So our goal is U hat of F2, the envelope of this universal enveloping algebra. And we know that since PGL algebras are commutative modular radical, it is very important to see on its commutant. And we begin with the commutant of the Lie algebra, free Lie algebra. It is well known from the theory of Lie algebra that the commutant of a free Lie algebra is also free Lie algebra, but now, for example, in this case, with infinite set of generators. These generators are iterated commutators. So if we denote the adjoint operator by 8x, so we to get G beta 1, beta 2, we applied at E2 several times, in fact, one more time than B2. And next we applied at E1 several times. And then we can write U of F2 as the tensor product of the commutative algebra in two generators and the tensor algebra of space E, which is the commutant of. And so this iterated commutators can be treated as a result of the action of non-commutative monomial in at E1 and at E2 on the first commutator. And so B is also the algebra of polynomials. And it is natural to expect that the envelope has a similar structure, but with C infinity functions instead of polynomials. And to see this, we replace the tensor algebra of a vector space by the formal tensor algebra of a locally convex space E. So we replace direct sum by the direct product, and the direct product of projective tensor products of copies of the space E. So this is the standard notation for the complete projective tensor problem. So we denote by C infinity F2 the following space. Tensor product of C infinity of R2 and the formal tensor algebra of S of infinity of X, where X again is R2, but in general case, X is not the same as on the left, the disjoint union of some manifolds of different dimensions. So I prefer to distinguish these two spaces, even in this case. So main theorem says that the multiplication on the universal resolvent algebra of F2 can be extended to continuous multiplication on this space C infinity F2. And in fact, the natural map is an envelope with respect to the class of Banach algebras of polynomial group. So proof is in two steps. First is that we without multiplication, we only to prove that there is a continuous linear map. And later you will see that in fact this map is a multiplication, not multiplication as holomorphism. And second, we find a homomorphism from U of F2 to some product of algebras BK, and each PK is a PGL algebra. And this homomorphism extends to the topologically injective map from C infinity F2. And moreover, we take as BK the algebras of C infinity with values in some triangular matrices. So this is the program. For the step one, we use a theorem on the classical ordered calculus. If we have finitely many elements of polynomial growth of a Banach algebra, then of course we can take each commutative monomial with some variables lambda 1, lambda m to the non-commutative monomial of b1, bm, but with fixed order. And of course, this map extends to the homomorphism from the another homomorphism to just a linear map from the algebra of polynomials to B. And the theorem says that in fact, since B1, Bm are elements of polynomial growth, then this homomorphism, this linear map extends to a continuous linear map. And the proof again uses Fourier transform. And I recall the definition of the space as infinity F2. So we have two factors. So we can immediately apply the theorem to the first factor as infinity of R2. For the second factor, we need a trick. First, we consider not the whole algebra T of S infinity of X, but just F as C infinity of X. This is a simple lemma that if element B of a real Banach algebra, and this Banach algebra is of polynomial growth, then the operator, adjoint operator ATP, is also because the polynomial growth are then an operator in the algebra of operators. And so using this, we can extend the action of the algebra of polynomials in E1, E2 on B to the action of C infinity of X. And I recall that monomials X and monomials at E1 and at E2. And also note that in this form of the algebra T of S infinity of X was defined in such a way that it has a useful property for maps to nilpotent Banach algebras. But we know that the radical, the commutant is in the radical, and the radical is nilpotent. So we can use this property here. And so combining all this, we get a continuous linear map from the tensor product from this space. We have continuous map for the first product, the first factor, and the continuous linear map for the second factor. So now the second step. What we need a homomorphism from our algebra. In fact, a second of homomorphisms for some algebras of C infinity with values in triangular matrices. But this homomorphism must extend to topological objective linear map. We can treat the homomorphism to such type of algebras as a family of homomorphisms from initially algebra to triangular matrices, but with parameters that smoothly depends. So homomorphism smoothly depends on parameters. And also we want to get a topological injective map. So we also do this step by step. So first step is when k is 0, and then we consider the map from F2 to those functions in such a way that generators take to the generators of S infinity of R2. So in fact, it can be, of course, extended to S infinity. So in fact, to as I as a. So and next we consider the case K1. So means then when we multiple C infinity of R2 on C infinity of X, and consider a family of homomorphism. To the algebras of triangular matrices of order 2. So we have a freedom to take this homomorphism, but this variant is rather simple. So for fixed element X, which have two coordinates S and T, we have two matrices, this one and this one, very similar. And it is easy to see that if we denote this matrix by Q, matrix with 1 in the upper left corner, then the theta X of the first commutator is just a multiple of this Q. And iterated commutators is also multiples of Q, but the coefficient here is a monomial up to t minus s. And so we need also to include some freedom for not only for x, but for R2. So we add scalars to these matrices. So we map every generators to lambda I plus theta x of I. And also it's easy to see that in this case, E1 and E2 acts as scalar multiplication. And combining all this, we have that when we apply this new homomorphism to element of, in fact, these elements of this form are a linear basis for U of F2. And so we apply it for elements of this linear basis. We have this product. And when we consider the result for polynomials and next for smooth function, we see that just we have a function with some linear change of variables multiplied by task t minus s and 2q. And so if we restrict this map to the product of S infinity of up to S infinity of x, we have a topologically injective map. Why? Feel that if we make a change of variables like this, of course, we have just an isomorphism of S infinity. And also, this map is injective. And moreover, this well-known fact, which is rather simple in this concrete case, that the idea generated by some finite number of polynomials in the algebra S infinity is closed. So the range of this map is closed. So injective and closed map, and we have Fréchet spaces. So this map is topologically injective. And moreover, theta x of g beta 1 beta 2 is a multiple of q. But q squared is 0. So this product is 0. And so it means that p1 is higher degrees. And so we have that p0 and p1 induce the map from first two factors in the big whole space to the product of these two algebras. And this map is logically injected. And so we take the case when k equals 2. So we'll use this matrices of the 3. And then it's not hard to see that we have a similar situation when we apply this homomorphism for iterated commutators. We have a matrix with 0 diagonal, non-zero second diagonal, and something in the corner. And when we have multiple two matrices of this type, then the element in the first place of the first matrices multiples of the element of the second place of the second matrices. And all this go to the corner. And so we have a similar formula. And so as before, we can show that we have a topological objective homomorphism, and after some additional reasoning, we have, in fact, we have a topological objective homomorphism for all this space, not most at this point, but continuously linear map. And so we have that this space is a closed subspace of this product, but restricted to the algebra U of F2 is a homomorphism. And so, in fact, we have a multiplication on the left space, and this space, in fact, is a algebra. Moreover, this is a PGL algebra because the right of the right we have a PGL algebra. Yeah, so in fact, this completes the step 2 of the proof. So we have a description of this envelope of this algebra. I recall that U of F2 in fact is a free algebra. And how we use this information? For example, we use information for Hopf algebras. Pirkovskii proved that if H is a Hopf algebra in usual sense, then its Arens-Michael envelope H hat is a topological Hopf algebra with respect to the tensor projective tensor product. But what about H hat PG? What's in case of real algebras? I recall the main axiom of Hopf algebra. So here delta means multiplication, S is antipode, M is multiplication, U is a unit, epsilon is a quotient. But in this diagram, it's essential that H times H is an associative algebra. And when we consider the analytic case and take the projective tensor product instead of algebraic, we get topological Hopf algebra. And here, the projective tensor product of H and H is an associative topological algebra. And moreover, if H itself is an Arens-Michael algebra, so is H times H. But for PGL algebras, there is a problem. In general, the projective tensor product is not compatible with the class of Banach algebras of polynomial groups, and of course for PGL algebra. But nevertheless, we can prove that we have no problem if we take algebras that is closed subalgebras of product of some C infinity from M to TP, some manifold M. And so in this case, A times A2 is also closed subalgebra in the product. And this tensor product is a PGL algebra. And I recall that in the proof of the theorem, main theorem of the structure of C infinity of Fk, we have algebras of this form as closed subalgebras of a product of the algebras of this form. And moreover, we also can take quotients of such algebras. It also needs some arguments, but nevertheless. And so I recall that a quotient of C infinity of Ak, a quotient of this commutative algebra, is called the C infinity differentiable algebra. So the algebras that formed not only for manifolds of some spaces with singularities. And we can consider non-commutative version. And we say that the quotient of C infinity fk for some finite k is a finitely C infinity generated algebra. So the term is by analogy with holomorphically finitely generated, written by Pirkovskii. And so, back again, then you see that we have no problems with tensor product in the case of quotients of C infinity of fk. And it is natural to consider C infinity finitely generated Hopf algebras. So a real Hopf topological algebras that are finitely C infinity generated. And the simplest way to get such an algebra is to apply the envelope. So if we take a real Hopf algebra that is finitely generated as an associative algebra, the term is affine Hopf algebra, then there is a unique real Hopf topological algebra structure on the envelope, and such that the natural homomorphism becomes the homomorphism of topological Hopf algebras. But of course, this is a simple example. But finally, I show you some advanced example. Take some parameter h bar, that is a real number that is not zero, and denote by C infinity af1 h bar. af1 means the Lie algebra of the Lie group of affine transformation of the line, which has two generators x and y with this simple relation. The commutator of x and y is y. But our algebra is a deformation. So we take the universal finitely infinity generated algebra with two generators with deformed relation. And then it can be shown that, in fact, this C infinity finitely generated Hopf algebra with respect to the multiplication per unit and antipode will be determined by these formulas. And note that here that formulas for y is not formed, but for x deformed. So for delta of x, we replaced 1 by these exponentials, and for s of x, we add an additional sum. And so in the end, some possible new directions. What I want, what I think that needs to be done. First, try to find some differential geometry constructions for free simple algebras. And also, I consider the case of free algebra with finite number of generators. But the question is how to describe in the case when you have infinitely many generators and moreover some infinite dimensional locally convex space as a base. And also I recall that we used the class of Banach algebras that dimension representations. This is also true for PGL algebras, which are projective limits. So the desire is to weaken the definition to include algebras with reducible representations of arbitrary dimension, not at least finite dimension. So I finished because my short talk it's midnight in China. So then, thank you very much.
Thank you very much.
Thank you.
Are there any
Спасибо.
questions or comments?
Yeah, please. Well, Oleg, do you have sort of integral representation for your non-commutative C-infinity calculus? Could you write down something like formula unique just as an integral, like Fourier sort of? Is there something like that, or I mean, you're so C-infinity
In fact,
calculus?
yes, because I use autocalculus, and this autocalculus is given by Fourier transform.
Yes.
So
Okay.
we can write
Yeah,
formulas.
sort of getting integral and tensoring by somehow, right? Just blowing up by somehow,
Yes,
I
yes,
guess.
yes,
Okay.
that was some formulas of including Fourier transform. Yes.
Okay, yes, thanks.
More questions, please. Well, I have a question. So the algebra you've constructed at the very beginning is a free analog of the algebra of smooth functions on Rn. So my question is, are there natural candidates for algebras of free C-infinity functions on more general open subsets of Rn? For example, on the ball.
Yes, I think that there is some set of special representations of triangular representations of algebras with topology. So, and we can take some algebras on some open subsets. Yes.
Thank
But
you.
no, this is another story.
Okay.
I guess it's not a sheaf yet, right? It just by somehow we can restrict to some open sets. But far as I remember, is getting a sheaf is a bit complicated here as well.
Yes, I hope that there is a shift. Yes.
Is it? Yeah, as I guess if Lie algebra should be or maybe 3 or 2 variables, I'm not sure. Yeah, if you want a sheaf, it's fine. Yes, good.
But of course, the irreducible representation is insufficient
Yeah, yes.
for algebras. But we cannot use the irreducible representations of dimension greater than 1. So I want to use triangular representations. No, here triangular algebras, triangular matrices is so basic that everything is based on them.
See, okay.
Thank you. So any more questions? Well, if not, then we thank the speaker. Thank you, Oleg.
Thank you.
For the very interesting talk. So next week, our speaker will be Yulia Kuznetsova. I don't know the title yet, but she was going to tell us something about Lie groups, but I don't know the details yet.
Yeah, okay.
Okay, thanks everybody.
Yes.
Thank you.
Bye.